friends. In today's video, we will be learning about image smoothing techniques like mean filter. So mean filter is simple and intuitive to reduce noise from your image. So let's assume we have a single layer image with pixel values as 10, 0, 20, 10, etc. And we have an average kernel of 3 by 3 size. So here we will convolve 3 by 3 average kernel on the image. What I mean by that is we will place the kernel on top left corner of the image and multiply each element by the kernel value and sum the output. So here we'll add 10, 0, 20, 20, 10, 10, 30, 15, 0. So we add these values and we divide it by 9, which is number of elements. So it comes up to 12.77. So we take a fresh image and update the pixel value to be 13. After which we shift the kernel to right and do the same process. So we sum these numbers, divide by 9 and put the value here. And we do this in the horizontal direction till we hit the end, and we shift one pixel downwards and continue going to right. You must have noticed that in vanilla version our dimension of image reduced from 6 by 6 to 4 by 4. Here is the simplified version of the formula where it is height minus kernel height plus 1 into width minus kernel width plus 1. So in our case they are same. So it is 6 minus 3 plus 1, which is 4. So our image is from 6 by 6 to 4 by 4. So if you notice here, if you use kernel of n by n, the dimension reduction will be n minus 1. Now let's talk about some ways where we can keep the image size as same. Because if you have a conventional computer vision pipeline or you are using deep learning, it is a good idea to have the image size as same and not changing with respect to kernels. So one of the method is the corner pixel will only have 4 elements to average. So you see here we just average these 4 elements divided by 4, so we get 10. And edge elements will have 6 values to average. So you see here this 0, we'll average it through these 6 values, divide by 6, and we'll update the value here. Also, there are other techniques where you can add zeros in your rows and columns around the image, which is known as zero cushioning of the image, or you can repeat last pixel row and columns and replicate it on all 4 sides. So you see here all these values are being replicated here and all these values are replicated up. So here your image size became 8 by 8, and now when I implement my mean kernel, it will be 8 minus 3 plus 1, which is 6. So I get my image size to be 6 by 6. So now let's talk about drawbacks of mean filter. Here, a single noisy pixel may affect neighboring pixel values, and we will see small patches of non-uniform color in an image. And secondly, due to interpolation, we lose sharpness of edges. We can mitigate these drawbacks by using other filters. So for now, let's see the implementation of mean filter. So this is an example of input image, which is sharp and without noise. In order to see the effect of our filter, we will generate Gaussian noise of same size as input image. We add the noise to our input image. In order to remove the noise, we will use mean kernel that we learned. Now, if we pass 3 by 3 kernel through the image, we see the effect of noise in neighboring pixels. So you can see here there are zombie patches of different colors which were not present in the original image. This is exactly what we saw as our first drawback of mean filter. Here we use a 39 by 39 kernel, which is huge, which will reduce the noise So you see here the noise is reduced, but you will lose lot of sharpness. This is our second drawback. Hence, we have a trade-off between reducing the noise and losing sharpness. So let's see effect of slowly increasing kernel size on noise and sharpness. So this is our input image with noise. So now we slowly increase the kernel size. So here we are increasing the kernel size. So this is kernel size 9, 11, 13 and so on. It is slowly increasing. We have reached 25. So you see here the image is getting blur, but noise as well is reducing. So this was all about today's video. Do like to make YouTube happy and subscribe to Soft Illusion for more such content. Thank you.